Works better. Okay. Welcome to a new room. Yay, it's bigger. So just a quick announcement. This is on. Can everybody? Is that better? I feel like there's a speaker in here. Maybe it's just me. Okay, anyway, we'll just go with it. I'll just have to get used to this new room. Yeah, I hear the echo too. That's the thing that's kind of thrown me. For those of you who are in here on accident and you're taking something like operating systems, you have switched rooms with us. So if you are in operating systems, you are welcome to stay and have fun with us, but it's probably not going to be what you're looking for today. This is Applied Math 4300, Introduction to Computational Methods, Numerical Methods, things of that nature. So, sorry. Hopefully there's enough seats. It looks like there's a few empty seats, so everybody who can be here can be here. So today we're going to finish up kind of the introduction to things, as well as kind of do a very quick introduction to Python, NumPy, and Matplotlib, all of which is on the homework. Hopefully you guys have looked at it. We will go over some of the options for installing Jupyter and running it. So if you haven't gotten that done yet, you have some options suggested. Yeah, so today's actually going to be a bit more informal than usual, actually even. I'm going to move the water bottle. In that we're going to be doing just a lot of simple coding inside the Jupyter notebook, so you can partially so you can see how to interact with it, some of the pitfalls, some of the things that are there for you, but also just to give you a very brief introduction to some of the core ideas. And I'll try to emphasize certain things that in particular will be important into the future. But before we get started with all that, does anybody have any questions about the course so far that you want to ask, raise? I have a couple announcements too that I just thought of. Okay, so CampusWire, please use it. There's been a couple questions up there. If you're not on it, if you just got into the class because you've been taken off the wait list, I have to do everything manually with CampusWire, so just be aware that it might be a little bit before you get on there. You should just receive an email invite. The videos of the class, if you're in the class, are available now. They will be posted. These are just the CVN versions of all these the lectures as well. And these will be ongoing, so if you do miss a course, a class or something like that, don't worry about it. It'll be up there. I generally encourage you to come anyways, because my personal presence in the room is, of course, not worth missing. But no, I'm just kidding. No, so it's out there for you, just in case you can't make it to class. Just don't worry about it. It's there for you. Okay. I think that's it. Yeah. Do you have access to these? Yes, they're on GitHub. So I think I posted something on CampusWire about that, the link to it. It's also on the syllabus. Any other questions? I have been getting a couple questions about where to turn in the homework. It's on Courseworks. You click on the assignment's available as a download, do the Jupyter notebook, fill it out, and then you upload it back into Canvas Courseworks when you're done. Okay? If you're in a wait list, where should I upload the course? You have to wait until you're in the class. So that's actually a good point. If you are on the wait list, feel free to do the homework. It's why I actually sent a copy out to you. If you're on the wait list and you didn't get it, let me know. I will send it to you. The reason why the homework is due the Monday after the drop add deadline, is because everybody in the class who's going to get into the class is going to know by then. So if you come off the wait list, you're free to upload it anytime you want. Okay. Any other questions? All right, so let's begin. So again, Jupyter Notebook. I'm going to probably make my Jupyter Notebook look a little bit different than yours, just so the text is bigger. Hopefully, is this lighting okay for everyone? It was a little bright before. So I'm going to make this a little bit different. This is just taking off the Chrome so I can blow it up. It's easier to see. But just know that I basically have the same interface that you're going to have. And you can toggle a lot of this stuff with the view. And then I can make it bigger, very big. So we kind of left off just talking about where to get the notebooks and things. So the question just asked, of course, this is a self-referential thing because I'm nearly certain this mic is on. That bothered me. Is there a button on it? We'll try that. If you can get to this, this notebook, then you would know where the notebooks were. So just to put that up here for you, the link is github.com/Mandley. It's me. And that's /intro-numerical-methods. It's kind of important that I make that bigger. Let me do that real quick here. There you go. Oh, put an equal sign. That's where all the notebooks are. And I'm updating them as we go. In fact, there's updates already. So just be aware. I will be probably correcting mistakes, adding new material, subtracting material, whatnot, as we go along through the course. Okay? So I'll leave this up at the top for a little bit by cleverly tiling my screen. All right, so the kind of the last piece of this first introduction notebook I did want to go over is ideas on how to install this business. There's two options. I think doing both is great. Installing it on your own machine means that you always have it. You don't have to worry about internet connectivity issues, things of that nature. It's also probably going to be faster to some extent and have the common interface that we all have. So there are some benefits to that. But there's also a lot of cloud services that are coming up that are absolutely free that you can also use. It doesn't really matter much to me. So there's actually, I just found today, this Notebook Quick Start Guide. So this actually links to how to get started, including an installation step. So if you want to know more about Jupyter Notebooks and things like that, there's a lot of different ways to install it here. So take a look at this as you want. Oops, wrong one. There's also something called Anaconda. This is just a Python in and of itself. It's pretty common. It's actually the versions of, on any of the CUIT lab machines that you're going to get is Anaconda 3 point something. I don't know what version they're up to yet. But it has lots of different scientific engineering packages available as part of it. So it's actually kind of a nice way to get at this stuff. Very similar type of idea is something called Canopy. It has a bit more of an IDE that's independent. So it's a development environment independent of the Jupyter Notebook. You can use that too. It has Jupyter as well inside of it. So either of those are really great options. You can also just install it directly on your machine if you are a little bit more brave to actually handle that type of stuff, either by the command line or there's lots of different Windows installers as well. And then just another thing, just remember to grab the 3.x version, so 3.6 or something, I think we're probably up to as most of these releases, but 3 in general. So in particular, if you click on Anaconda here, it'll take you to this page. This is not the version number you care about. It's the version number down here. So I have a Mac, and you can see there's 2 versions, Python 3.6 and Python 2.7. Pick 3 point whatever that is. Okay. So this will give you an entire installer to install on your machine. If you already have Anaconda, oftentimes you can just go, and you only have 2.7, for instance, you can grab 3, and you just have to make sure that you're using the version that you think you're using. So if you're having troubles with any of this, come talk to me during office hours or either the TAs as well. We can try to debug with you. So that's on your own machine. There are also multiple newer versions of things on the cloud. This is changing a lot. The Google Collaboratory, I have to say it right, is a research piece that Google's been working on. Recently made it available in the past year. And it is actually just Jupyter notebooks with some crazy GUI placed on top of it, but they're just Jupyter notebooks. You should be able to download them. They have most of the tools that we're going to use this semester, so it's not too big of a deal that way. Not to be undone, Microsoft also has what they call Azure notebooks, which is actually Jupyter notebooks, said behind it, all that stuff. So both of these are available, and there are free versions of both of them. You have to sign in using the correct credentials, but let's see if this actually does what I think it's going to do. Maybe not. Note that they are very careful to say that these are either in preview or in beta. So I don't actually know what that means. Things seem to work fine on both these platforms. They do look a lot different than what I'm going to be showing you, so just so that you know about that. But this isn't going to work apparently for me. The other platform that is available, and it is free as well, is called CoCalc. CoCalc was actually something called Sage Math Cloud up until about a year ago. These guys have been around for a very long time. They're actually probably the progenitors of the Jupyter Notebook, and they use Jupyter Notebooks all the time. So feel free to use that. They use the generic Jupyter interface to it. But it's also free unless you want to do some heavy computing on it, which we won't need through this experience. Okay, so the last thing I want to say is to class, bring your laptop. I see many of you have done so. I highly encourage it. I'm really glad we're actually in this room because I think there are actually plugs a little bit more scattered throughout the room than the other room. I don't know about this beginning area, unfortunately, but I think there's more plugs in the stadium seating. So try to bring your laptops charged. That's always a kind of a problem. The point of this, though, is that I'm going to periodically have you work on a problem with your neighbor and yourself before I go and give you the answer. This is mostly to try to give you a chance to catch up with what we're doing, have a chance to actually see if you can implement something without me just telling you the answer, and also to see if you can, with a neighbor, perhaps figure out what it is we're trying to do at the time. So you don't have to listen to me lecture the entire time as well. This is nice for me and probably you as well. But these don't really work unless you are actually bringing in a laptop or something that you can actually work on with Jupyter Notebook. So please bring laptops. I can't see any of your screens, so if you're surfing Facebook at the time or something of that nature, I'm not going to judge you because I can't. But just bring your laptops. It's also really nice because then you can actually go through the course notes as we go through them. You can run the code that I'm going to be putting up and writing, and you can play with it as we go as well. So that can be actually very useful as well. Okay. Any questions on any of this? All right. I think this might be a little big. All right, so introduction to Python. So we're going to cover a bunch of stuff, and I'm going to go very, very fast. If you're getting stuck with something, raise your hands, and I'll try to answer questions that you have. Some of these things, it's just playing with them, getting used to kind of some of the syntactical things if you're coming from a different language. And those of you who already know Python, bear with me. This is going to be kind of boring for you, or maybe you'll learn something about data types. You never know. So the first thing about Python I do want to kind of emphasize is the import mechanisms. So this is how we tell Python to import libraries, that it won't import by default. This is a weird one, so don't necessarily take this one. This is a way that we're actually allowing this to be backwards compatible with Python 2, actually, because the print function in Python 2 differs from Python 3, and so does dividing. And I'll talk a little bit about why division has changed a little bit. But just so you know, that is an import statement, and we'll be using those a lot. And the other thing, too, I want to say is there's also a lot of other introductions to this material. So if you do feel a little bit lost, take a look at these two links. They're either basic Python, or there's actually this software carpentry does have some numpy pieces to it. and also a lot of other things you might find useful if you ever want to use this for your research or work as well. Okay, so Python math. Python can do math. Being a programming language, you kind of hope that that's true, but not all programming languages can do math. I know it's weird. So we can do simple things. So 2 plus 2 is 4. Okay, so in the notebook, this is the type of thing. We have a code cell here. So again, this is a code cell, and I made my, does everybody have this URL? Okay, I'm going to get rid of this, actually. So I'd have a little bit more space. Where'd my mouse go? So I'll leave this up here just for right now. So note that, again, I'm selecting this cell here, and it says code, which means that it's an executable code of some sort. This is Markdown, so that's going to turn into text or LaTeX. So just keep an eye on that. So 2 plus 2 is equal to 4. You can see I've executed, this is the second thing that's executed in the notebook. The input in square bracket 2, and the output is 4. Okay? If I execute this again, it turns to 3. So this is actually keeping a running tab of the actual output. And if you would like to, you can refer to any of the input or output using that number 3. Don't do that, if at all possible, because note that if I execute this next cell, it's 4, and I go back here and do 5. Now it's out of order, which is another thing to be worried about. But also, if I then re-execute this, now it's 6. It's no longer 4. It's been 6. And if I restart the notebook, then all the numbers disappear as well. So although you can do it, try not to. That's a very dangerous thing to be trying to do. But ever onwards. So here's another more complicated thing. We have, order of operations going on here. Hopefully everyone knows about that. In Python, to do powers, it's asterisk, asterisk, not caret. If you do caret, it does something else. So if you're getting weird answers, that might be why. This is -4. Here's 1/2. So this is where Python 3 and Python 2 differ. So you take 1, you divide it by 2, you get 0.5 out. Seems pretty straightforward. But in fact, in Python 2, this would not have given back 0.5. It would have rounded, floored it, actually. So if you are getting weird results like that, it's probably because of this. So when you're typing these in, Python is interpreting this 1 as an integer, and that 2 is an integer. And in 2.7, it thought that you would, by default, want an integer back. And it can't give you an integer 0.5, right? Unless you tell it more so. Okay? So if you are deciding to use 2.7, just be aware that you're probably going to run into this. The best thing to do, I find, is to just usually write these as like this, and then it would give you the same answer in Python 2 as Python 3. Okay? But for Python 3, we don't have to worry about that so much. Same goes with this. We can use all sorts of different things for powers that can be 3/2, for instance. Here, I'm just being very careful about using floating point numbers. Sometimes the division is not recognized as being a floating point number, so you do actually have to be a little bit careful about that too. The thing that I've just learned to do at this point is to just always put 4.0 or 4 point after a number that I know to be a floating point number. I want it to be a decimal number, and then it automatically takes care of it for things. So there's a lot of actually examples here of different data types in Python. Mostly we're going to be dealing with integers and floating point numbers. Floating point numbers we're going to talk about actually next week, why we care about floating point numbers. At this point, just think of them, they're just decimal numbers. They're numbers that have a certain number of digits after the decimal point, certain number of digits before the decimal point. There are also other types of numbers. There's complex numbers, which we'll talk a little bit about today. There's also something called a decimal number, which doesn't make sense until you've learned about floating point numbers, so we'll talk about that. There's also actually explicitly a fraction data type as well, so it stores fractions properly. There's all sorts of things like that. The complex numbers we will see a bit more of, so here's an example of that. So kind of coming from more of the electrical engineering field. we use j as the imaginary number. So this is 3.5i in mathematical speak. And that's exactly how you write them. That's how they'll be output. OK, so this is kind of boring. This is like basic operations. That's all well and good. We're going to do that a lot. But we're also more interested in some more complicated things. So here's our first kind of import statement, import math. This is the generic Python math package. So inside of this thing is a bunch of stuff, including square root. So square root of 4 gives us back 2. Notice it is in a floating point number, as a floating point number. Math has also changed a bit from Python 2 to Python 3. By default, I believe if you gave it a integer, it would have provided you with a floating point number, or excuse me, an integer as well, if it could. But in this point, I think everything's floating point coming out of these things. And there's other things. So if we want to take the sine of pi over 2, so the constant pi is in there. Or the exponential of pi divided by 4. So this would be e to the negative pi over 4. We get some long number approximation of that value. All right. So there's lots of different things in math. One nice thing that we can do is after we have imported math, I'll add. If you ever want to go explore what's inside of math, I can type math dot, like I was actually going to call a function. So at this point, I could write sin to get sine and stuff like that. But what if I just wanted to see what was available to me? In the Jupyter Notebook, at this point, if I push tab, I get a list. So arc cosine, hyperbolic arc cosine, ceiling, degrees, error function, factorial, floor, the gamma function. I have no idea what that is. Infinity. Infinity has a special representation. You could ask if something is infinite, or is finite, or is infinite. All sorts of things, different log functions. There's a lot of stuff in here. Okay. The other thing you can do. Oops. That is a interesting thing. In the Jupyter Notebooks, you can also do math question mark. And if I execute that cell, now it gives me actually this dialog box. If you click this button here, it'll just, oh, that's completely unreadable. So this is the doc string for the math library. Unfortunately for the common Python modules, it's pretty unhelpful by and large. So this module is always available. Fantastic. It just comes with Python. And it provides access to the mathematical functions defined by the C standard, which, unless you know the C standard, is probably not a very interesting revelation. So there's lots of things we can do. Most of the time, we're not going to use the math library, so this isn't too big of a deal. But there's all sorts of things we can also do. Oh, it's not going to show it to me. That's too bad. I'll show that to you later. 2 question marks actually brings you to the actual code. If the code's available, and it's not just a compiled binary, which is this case, you can actually see the actual Python code, which is kind of nice. Delete that. So this is the import math statement here. That's where we're getting all these math functions. The other form of the import statement is from math import star. So this means that I want you to take everything that's inside of math and import it into the local namespace. So what that means is I can call sine without that math dot business in front of it. Okay? So it looks nicer, and it's a little bit easier. I would put a caution on doing this. This means that sine, e, all sorts of things will be defined without that math in front of it, which means if you ever define a variable called e, for instance, it'll be whatever that variable that you defined it as, not e as in the exponential function, or exp, I guess, actually. So the benefit really here is so that you don't accidentally create a bug in your code where you actually accidentally assign exp to something that's not the exponential function. And it also makes your code a little bit more readable. We're going to use a different library other than import math in a little bit that has a lot of the same functions. So if you're ever curious where that function's coming from, having math dot whatever in front of it tells you right away, well, that's from the math library. There's ways to break that too, but it's much more clear. Okay? So I suggest that. Variables. Any good programming language has variables. Here I'm just defining num students 80, which now should be 110 so shortly. Room capacity, this is kind of an entertaining example that didn't actually change from last time, has eerily accurate. And then we can act on those variables like you would expect. So this gives me some percentage of the total capacity, or how much is left, actually. So that's just manipulating variables, equal signs, and things like that. All modern programming languages uses that. So here's kind of the first thing that is a little bit more Pythonic. And we're not going to use much with lists, but we're going to use something that looks like a list a lot. And that's a numpy array. So this is a simpler version of that until we get to that. Okay, a list is like an array. Right? It looks like an array. It's a much more generic thing than that. It's an ordered set of objects. Here I have grades. So all these objects are the same. They're all floating point numbers. So that defines it, these square brackets. There's also something called a tuple, which is defined with round brackets, so parentheses. The difference between the two is that you can modify this thing. You cannot modify a tuple. So it's, there's various reasons to do that. We're not going to care so much about that. Just use lists if you need to. So we can do all sorts of things. We could index into this list, okay, just like a regular array. So grades 3 means that it's going to give me back 76. That could be somewhat counterintuitive, but the other thing to keep in mind with Python is that it's 0 indexed arrays. So this is just like C. This is the 0th element of that list, the 1st, the 2nd, and then the 3rd. Okay, so this is really the 4th element in that list, if you want to talk about that. So everything's going to start indexing at 0 and count up from there. There's other nice ways to index things. So -1, it wraps around. So -1 is going to be the last element on that list. So 70. In fact, I can keep on going. If I wanted the second to last, I do -2, it gives me 98. And it continues to wrap around. So there actually, you could think of the indexing starting at 0, but then you go negative, it then just wraps back around. And if you go positive, it goes forward. If you go forward and you go too far, it'll warn you. It won't like you. If you keep on going backwards, it'll also eventually complain to you. So be aware of that. But that's a nice thing. You can get refer to the ends or the beginnings of lists that way really easily, regardless of the length of the list. Speaking of the length of the list, LEN stands for length. Tells us the length of that list. So it says 6. There's 6 elements. Note again, because of the fact that we're indexing by 0, if I put 6 into grades, it would complain to me. That's past the end of the list. So if you want to index the actual end of the list, you would have to do length of grades -1, and that would give you 5, which would be the end of the list. Or you can use -1. Oops, just hit spacebar. You can add values to a list. So this is a kind of a syntactical nice thing. So here we have grades, and I'm going to add 62, 82, 59, and the list of those things. And then I'm going to print it. So here you can see I've appended 62, 82, and 59 from that. Okay. If I was going to type, we'll do this. Note that it doesn't like that. It doesn't understand how to add an integer or a floating point number, like a floating point number, to that list. There are two different types of objects, and it just doesn't like it. But if I turn that thing into a list by adding square brackets, it's quite fine with it. Okay? I've also been keeping on adding the 62, 82, 59, so my list has gotten actually quite big. Another thing to just keep in mind, just to make some stuff a little bit more clear, you can also shorten this into, if you're just adding something to a list to itself, you do plus equals, that works the same way. So lots of different languages use that syntax as well. I'm going to make this shorter now. So now I'm going out of order. I'm going back and re-evaluating things. So now I get a little bit more manageable of a list. Okay, so one of the biggest things we're going to be doing in here is slicing. Slicing just means that we're going to take a list or eventually an array, and I want some portion of that list or array. The way this works is you give two numbers or one number. In this generic version, we get 2:5, gives me 85, 76, and 98. So 2 is referring to the first index, so 0, 1, 2. Okay, so it's going to give you 85, 76, and 98. And so 0, 1, 2, 3, 4, 5 is 70. So another very important thing to remember in Python is when you have the ending integer in any kind of range like this, it's going to go up until that, but not including. It excludes that last piece, unless you explicitly tell it. So if I really actually wanted to have 70, I would actually have to use 6. And it would give me 70. Okay? So very, very common thing to accidentally make bugs. I do it all the time. You just have to be careful about what you're indexing. Other than that, you can actually index all sorts of different ways. So 0 to 4 would just give you the first 4 values. So 0, 1, 2, 3 would be the indexing. Here's another nice thing. If you wanted to index from 0 to 4 and you didn't want to type 0, this gives you the same thing. So :4 gives you everything up until the 4th index. And vice versa, if you did 4 : whatever, it takes the 4th element on and gives that back that. Okay, so you can take one index and then have either the beginning or to the end to do it. There's other ways to do these indices. For instance, you can actually have 3 numbers in these colons, and you can stride through the list. So if you wanted to go by 2s, sometimes that's useful. There's lots of different ways to construct this. I generally find if you are trying to do something like this, just print it out and just make sure you're getting what you think you're getting, because otherwise you can get into trouble. Because one-off errors in this are very common and hard to sometimes remember or debug, especially if you have errors where you're going beyond the end of the array and you're like, well, why, this is the same size array. It's like, well, check to make sure that that's the case. So this is a weird thing. So if you look back up here, 4 to 11, the 0, 1, 2, 3, 4, 5, 6, 7, 8. I should only be able to index this up to 8 or 9, actually. The reason why I can go beyond that end is because it's just checking until it reaches that end of the array. So going beyond the end of the array with this slicing doesn't matter. It does it quite fine. So just be aware of that. That can also lead to big bugs, because if all of a sudden that array became bigger than 11 or 12 or 13, then you're actually not getting the entire array anymore, or list. So that's some slicing. This is probably going to be one of the biggest things to kind of figure out how to do, just because it's going to be really, really useful for us in a lot of different situations. So I've been talking just in terms of numbers, and that's mostly what we're going to be using and thinking about. But just from the practical standpoint, a list actually can contain anything. And it doesn't have to, one list can contain anything inside of it too. So here we have a 2, a string 2, a 2 that's an integer, and a 2 that's a floating point number. It doesn't care anything about that. So I actually can get rid of this int part. So that is just a string 2. A string is just text. Doesn't know what's going on there. If I do use this int thing, this tries to make coarse or cast, as we like to say, more computer science-y things. This tries to turn whatever's inside of that thing into an integer. And in this case, it knows perfectly well what 2, the text 2 means. It means 2. So it's going to turn it into the integer 2. Don't rely on this. Yes, it's pretty specific to various strings. So just be aware of that. We could also do all sorts of other things, like if we wanted to really have a list of lists, make it more look like a matrix, or in this case, maybe a column vector, you could think of this. You can do this with just putting lists of lists and things. In fact, you can do this infinitely. You just need more and more indices to refer to it. But here we can see, oh, did I not define this again? Okay. Actually, let's go back to this, though. We'll go back to the string 2, the integer 2, and 2.0. If I do this, you can see there's a type error here. And it's complaining because it doesn't know how to take the string 2 and divide it by 1. Okay? It would have to do some sort of casting to do this. So the reason why this works when I put an integer around is it does know what an integer 2 divided by the integer 1 should be like. Okay? So oftentimes, these type errors are very important just to read through. It'll hopefully tell you where it's happened. So that's what this green arrow means. And then it says specifically what it thinks is wrong about what happened. In this case, it's actually very useful. Sometimes they're not as useful as they could be. It's saying str, that's a string. In integer, it doesn't know what to do with those two objects, dividing by each other. But again, if I use, so just for completeness sake, we can turn it into a floating point number like this. And it knows what to take a floating point divided by the integer 1. And the rest of these also act accordingly. Okay. So lists can contain lots of different objects. I'm just giving you very basic ones. You can put all sorts of crazy things inside of there just to keep track of them. It's a nice way. It's an ordered set of things in general. You can also do stuff with loops. So we're going to talk about that in a little bit. But here's a simple for loop where it's going from the range. Range is another intrinsic command in Python. It's creating basically something that's generating numbers 3, 4, 5, 6. 7's not included, just like our business with the indices. And then inside the loop, it's putting those numbers into I and then printing out each of these. Okay? So hopefully, although the syntax might be different, this for loop business is familiar to you to understand what's going on. Any questions so far? Yes? We almost never will. There are some cases where it can be useful if you're trying to construct. Like I use it in plotting sometimes. Like if I want to have like 6 different figures, and each of those figures has something different it's trying to plot, I might create a list that I can loop through. So I run my plotting code once, but then it just fills it in like that. You'll see some examples later on, but by and large, we don't do that type of thing. And it's arguably not a fantastic thing to do, but it exists. Okay, control flow, if statements, for loops, there are while loops, things of that nature. So in Python, if statements look like this. So again, they're white space delimited. There's no curly brackets in any of this. So what that means is that when I write if x is greater than 5 colon, this is indented. Indentation has to be consistent. But once it's indented, it means that's all inside of the if statement afterwards. Okay, so I can actually continue to write things in here. I make this greater than 5. You can see that it gets executed. Else if, ELIF, that's how that works. And then else, of course, is the last statement on the if statement. So just remember, keep the tab delimitation or the white space delimitation the same. I tend to use for just because I think it looks a little bit more readable. But in all honesty, you can use anything you want. You just have to be consistent. So if you're copying someone else's code and modifying it, if they use a different set of white space, it may break things. It gets very confused. But that's basically what an if statement looks like. So we can change this again. Just get the obvious things to happen. Okay. For loops. So I said something about that up above. Here's another example. The range command in general is a nice way to just make a range of numbers. So here I'm going from -10 to 5 by increments of 3. Okay? So you can tell range actually takes a variable number of arguments. And this is a good example of it. If I left out 3, it automatically assumes I want to comp by 1. Seems reasonable. If I left out 5, well, now I'm not specifying enough for what we're going to do. But it basically does what you kind of expect. Note that it does the right thing. If the next three, it doesn't match exactly, it just ignores everything left over. So if you do need to stride through things, this could be a good way to do it. This is a little bit of a silly thing. Why would I want to print out numbers like this? You could actually construct an array or a list of numbers this way, or you could index into a list this way if you wanted to as well. So here's another example. Does basically what we had before. Here's a little bit more complicated of an example, and one of the kind of nice features of Python. Here I have a list of strings that are animals, but they're strings as far as Python's concerned. This function called enumerate, what it's going to do, it's going to say, I want to go through this list and put the strings from that list into animal, but I also want it to count. So if I want to know that cat was the first animal, so it's 0 indexed, it's going to put the 0 into I. So when it goes to dog equals the animal, I is going to be 1. And when it's chinchilla as the animal, I is going to be 2. Okay? So we will use this, because occasionally we will want to index into an array, and we also want to have what index we're on at the same time. Maybe we're indexing into a different array. So enumerate's great. Here, this is actually the modulus operator. So this is going to be if I divide I by 2, and it divides 2 evenly, right? That means the modulus would be 0. Okay? And that's when I want to print the animal like that. Okay? Note, 0 divided by 2 is equal to 0. So we do get that one, and we also get chinchilla. Okay? So it skips cat. So this would be if you wanted only the even numbers, for instance. That would work here. Or I could also do the difference and say not equals here as well. Okay? This can get as complicated as you want. There's all sorts of neat syntactical things. Don't feel like you have to use this stuff, but if you want to use it, use it so that your code's readable. But I think it's kind of fun, some of this. This is what's called a list comprehension. So instead of writing a for loop like we did here, this thing actually looks like a for loop syntactically. There's in the background, it's doing something a little bit more efficient than that. But basically, if I say for animal in cat, dog, chinchilla, it's going to do this for loop implicitly, and then it's going to say, I want you to take animal, and one of the functions that you can apply to a string is to capitalize it. Okay? Capitalize, it's not just uppercasing something. It's not just lowercasing something. It's actually capitalizing it proper. So that's a little bit more of a nuanced thing. For a list comprehension, you can see that this has actually got a square bracket around it. What it's going to do is it's going to actually create a list with the capitalized values. So whatever this is going to output is going to go back into that list. So if I do this, you can see cat, dog, chinchilla is actually capitalized. So that's the original animal new, which is exactly this thing here. Right? And then range new is the same type of thing. It's just another example of this. So for I in range 3.7, that means that this thing in front of here is actually what's going to be each element inside the list. So 3, 4, 5, 6 is exactly what it is. Okay? So those can be useful if you just have a simple thing that you want to perform a bunch of operations on and get a list back out. Those work great. Here's a little bit more complicated of an example. So here we're actually using some more of the for loop controls. We also have nested loops. We're going to use a lot of nested loops. So be aware of that type of thing. We're also going to probably break out of things occasionally. We actually will do that a lot in the beginning here. And we'll talk about that when we come to them. This is a very simple function in reality. It's just trying to check if a certain range of numbers are prime or not. And we're using the modulus operator again. So we're checking 2 to 10. Is prime is going to be true outside the loop. So this is a Boolean. In Python, you just capitalize the first letter of true or false. And then we go and check to see if the number we're checking, which is little n here, if the modulus of that with x, which is 2 to n, so we're not going past the number, so a prime number would be defined if something can actually divide into it equally. if that divides unequally, then we know that prime is false, and we print it, and we say what the common divisor is. Okay? And in that case, we've already found the common divisor. We don't have to check any more numbers, and so the break statement is used to break out of that inner loop and just continue on. We're done with that business. We don't have to check any more numbers. So then once we're out of this, then we check to see if is prime. So if that's true, then we say something is a prime number. Okay, so that's the type of logic. And it gives us back what we hopefully think it will. 2 is a prime number, 3 is. 4 is equal to 2 times 2. You know that. 5 is prime, 6 is equal to 2 times 3, and so on and so forth. Okay, so we could go higher as well with this. And this code would probably slow down after we got over a little bit. This is actually growing at an unfortunate rate in terms of computational requirements. But it does kind of what we expect. So the break statement, we're going to use a bunch. Again, it just breaks out of whatever the innermost loop it's in. There's also a pass statement. We don't really use it unless we're just putting a stub or like, you know, a placeholder in. It just does exactly it. It is a statement that does nothing. You'll see why we might want to do that. So for instance, if I wanted to put pass here, I have some function. This is how we define functions, which we'll get to. But if I want to remember, I just want to have that function name already defined, but I don't want to define it now, I write pass. It doesn't do a thing, but it's syntactically correct. There's some other additional for loop controls, and actually, I think the link here, you can actually see there's a nice set of operators. So here's the ones kind of just generically defined. So floor division, for instance, is a little bit of a difference on division. There's all sorts of comparisons. So not equals is the exclamation point equals, common. Less than, equal, things like that. Plus equals, minus equals, divides, exponential. Here's the bitwise operators. Don't worry about it if you don't know what these mean. You don't have to use these if you don't want to. You can if you want to, and understand what that means. So note in particular that caret does not mean exponentiate. It means binary XOR. So if you're getting weird things out, just be aware. And then there's all sorts of other things here that I'm not going to touch on too much. Is not is stuff you can put in if statements. These are usually used when you're checking to see if an object is equal to something else. We're not really going to use that too much. I will try to point it out when I have used it in particular times. If you're getting some weird statement about comparing things that doesn't seem to be working, you might want to try is. But this does not act like the equals sign. This is another one I did want to mention, in or not in. This is actually kind of nice in Python. You can say, if I had a list of, like, say, the entire alphabet, and I asked if, quote, A in my list, if it's the alphabet, then A is in the list, and it returns true. So it's a way to say, is this thing inside of a list or some other container like a list? So that can be a really nice way to check things like that. And then there's a bunch of other things here. So just a nice list of things there. Okay, so we're going to be defining a lot of functions. And if you haven't looked at the homework yet, a lot of the homework is defined by I tell you what the function name is and what inputs there are, and I want you to write the interior of that function. This allows us to do testing in an easier way. So let's talk about functions. Functions are just like any other language. They're subroutines or whatever you want to call them. They have this type of signature, so DEF, so define my print function is the name of the function, parentheses, whatever's inside of that is the arguments, and colon, and then again white space delimited. So anything that's one white space tab or whatever inside here is all going to be inside the function. So in this case, this function simply prints out whatever I gave it. So when I call it my print function here, prints out 3. Nothing too exciting. We can also do this where we have return values. So I have A and B are the arguments into the function, It's going to return a plus b. So it gives me 8. Give it 5 and 3. This is actually kind of nice about Python and some other languages. There's keyword arguments. So this is called a keyword argument here. So c is equal to 1. I'm calling it c, so it's the name of the variable, and I'm also giving it a default value. So if you didn't specify what c was, then it would automatically become 1. So here's 3 different ways to do it. So this first way, it's automatically 1. Second way, my crazy function, I'm saying I want c to be 2. So this works. Note that it's just in the order that they're specified up here. I don't suggest doing that because that's a little bit harder to read. What I generally suggest, if you do want to give a keyword argument, is to just say c is equal to 2. So you know exactly what c is. You can glance at it, and it's done. It's not so difficult to figure out. So here it actually is giving my output as a tuple, and that's because I'm putting it on the same line. So if I just call these functions, oh, that's not working. Oh, well. Of course, I got to print it. Oh, actually, let me show you a neat trick. We'll do this. All right, so you can you can modify more than one line at a time in a Jupyter Notebook. Okay, this is exactly when you want to do this. So what you can do is on the Mac, it's Option, Windows, it's Alt, I think. I'm going to drag this little cursor here, and you see the actual number of insertion points has multiplied to 3. And now if I type print, parentheses, it types it on every single line. And actually, I can continue with this. I've now gone to the end of the line by whatever keyboard thing you do, and I can continue and add a parenthesis. So now I'm actually done it all. Okay? Definitely very useful, as you can tell. So in this case, what I do is you hold down the Option key, and you drag. So if I dragged up here, you can see I'm getting all sorts of weird things. Oh, here we go. When you're dragging, it's best to probably be in a straight line. Doesn't necessarily mean you have to be. So you can kind of have this gigantic cursor going around. So if I was to push over here, you can see it's getting a little confusing to see what's happening. But there's all sorts of things like this. So if I wanted to actually indent this, I can select all these rows, and then on the Mac, it's Command bracket, indents it in, indents it out. There's all sorts of things. So there's lots of different tricks, editing tricks that can really save you a lot of time, just so you know. I think a lot of these are actually up here. The keyboard ones are up here. So there's lots of stuff. So be aware. It's fun. Learn new things. So now let's see if that actually works. So now I'm actually printing every single one. The reason why I was only printing out one is that by default, the Jupyter Notebook is only going to print out exactly what the last value was output. Because the rest of these I'm not doing anything with. So that's why I was just printing out 11. Here's another one. So here, the difference here is I'm returning multiple numbers. You can see there's just a comma in between each of these. What Python does is it wraps this back into a tuple. Again, a non-modified. You can't modify a tuple again, but you can index into it just like a list. So I'm just grabbing a plus b, which is 5, out of this. If I just printed x, gives me the tuple, gives me all the answers that I wanted back. Okay? So that's another thing. A lot of times what you can do, which is nice, is that some functions that we'll use from time to time will have multiple outputs. And if you just want one of the output, you can just grab one of the output using some syntax for that too. Let's see if I can. Is that it? Nope. I never remember what the syntax for this is. It changed. You can do it. Okay, so here's a little bit more of a complicated function, the Fibonacci function. So it's going to basically tell me what the Fibonacci sequence is. So here we go. Here it's actually writing it back out. So Fibonacci, if you recall, starts with 0 and 1 or 1, 1. And you add the previous two numbers to get the new number. So 0 plus 1 is equal to 1. 1 plus 1 is equal to 2. 1 plus 2 is equal to 3. 2 plus 3 is equal to 5, so on and so forth. This is surprisingly shows up all sorts of places. The golden ratios in the Fibonacci sequence, things of that nature. But this is just a function. It's going to return a bunch of values. Here we're using a while loop. So a while loop just takes and does the loop until that condition is no longer true. Generally, the danger of using a while loop is that you can go into an infinite loop. So just be aware of that. Most of the time, we're going to use for loops in here, but you can definitely do that. Here, I'm also using a different thing. So values is actually a list. That's the way I've defined it here. I'm using the append function to append to that list as I go. That's another thing. Similar to the plus sign, append does the same thing. A little bit safer. OK. So here's just some general other thoughts. Again, something that is actually a really useful skill to have is to kind of stick to a coding style and just adopt it. And here are some suggestions. This is actually Python's suggestions. So all Python code in the standard library and actually NumPy, SciPy, and all the things we're going to use abide by these ideas with some differences. I don't really care. As long as I can read your code, fantastic. So it's more out of consistency that you should go by rather than these things. But these are actually nice ways to do it. One thing I will say, please comment your code. Never assume that we know exactly what's going on in a line of code. You don't need to comment everything. Like if you have a comment and a line of code and you do each one of those, that's too much. Use it sparingly as well. Yeah. In the code itself. So comments, I would say, like if you have a particularly complex thing you're doing, it's best to just put a little comment that was like, oh, this is calculating this. Or if you have a block of code, you say, I'm now going to find the, project onto this basis. It just helps the person reading the code know, oh, this is projecting onto this basis. I should understand the code as that. It's up to you. I don't think it's a bad idea. By and large, again, most of the time we're going to be writing functions, or you're going to be writing a function, and the doc string is the way to do kind of the intros to things. I guess I actually got rid of that. Oh, I did have sorry, I skipped over that. This is the doc string. So if a string comes right after the definition of a function, that's called a doc string. That's where all the information about a function should go. And I encourage you to write those as well. But yeah. No, unfortunately, we're not using GitHub in that way. Yeah, GitHub doesn't play nicely with Jupyter Notebooks enough that I've figured it out. Yeah, it would be nice though, but it's through Courseworks. Yeah, just the way you downloaded it, where you found it, you uploaded the same spot. Yeah. Yes. Yes, but only in the sense if we can't figure out what your code is doing, then we will take points off. So it is important for us to be able to read it. Whether it's the fastest implementation of it or not also doesn't matter so much, as long as it doesn't take forever. If it's taking 10 minutes, I'm a very impatient person. I'm not going to wait 10 minutes, especially when it's supposed to take seconds. Nothing we do here is probably going to take more than 30 seconds. So. Yes, although you'll know exactly what cases those are, because we put them in the homework explicitly. Yeah, those are exceptions. That's just to tell you that you should remove those exceptions. You're getting ahead of me. That's okay. Those are good questions, though. Okay, so coding style, just take it. I mean, it's more just advice in general than anything set in stone. We also saw that there was some help functions and question marks. This actually is exactly when you write a docstring for a function, if you do a question mark or a help on a function name, that's exactly what it gives back out to the user. So we'll be seeing how to use those. And of course, Jupyter notebooks have all sorts of things with them. Don't put JavaScript in your Jupyter notebooks when you turn them in. It is a pain, and we probably will strip it out. Not that you have any reason to put JavaScript into your notebooks, but just be aware that you can. You can do all sorts of crazy things with these things. But yeah. So any questions so far? This is like the first classroom. There's not a clock at the back of the room to watch that. Yeah. So if you indent and unindent the Jupyter Notebook, especially if you use that hotkey combination, it will recognize what you're trying to do. So spaces or tabs doesn't matter, one way or the other. I would not mix them. That's the only thing I would say. I tend to use spaces because if you copy it to somewhere else, tabs can be viewed in different ways, whereas spaces, it's four spaces, it's four spaces. I'm not going to try to force any kind of spaces versus tabs type of arguments in here, but that is why I use it that way. So let's actually touch on the homework real quick here, I think. So for those of you who haven't actually looked at the homework, here's the homework in its unanswered form. So for instance, this is a question that I want you to do up by hand. And by hand, I mean type math into this. Again, what I would suggest is go up to this cell, double click on it, and you can see that I've actually written some LaTeX here for you. Copy and paste it and modify it. Don't rewrite everything. Don't learn from what I've written, because you can copy and paste this business down below, and you have something to start with. Okay, so you would just put your answer here. Same thing with these. Here's a coding question. So here's the not implemented error. So this is when we have exceptions or errors in Python, we say we raise an error. Not implemented error just means it hasn't been implemented, and we want you to replace that error with your own code. So it's more of so just a way to kind of remind you that you're supposed to do this. Because of course, if I actually execute this in the testing code, oh well, I gotta do this first. You'll see it's not implemented error, and that's just because it's not implemented. So if I was going to come through here and actually implement this, I would erase those two things and then put my code right there. Okay? So, I mean, we can see what happens. This is wrong. So now it gives you all sorts of business. This testing, oh, I didn't put that. Whenever you see testing, numpy.testing, what I'm doing is I'm using your function, I'm calling your function, and I'm checking the answer that I want to get back out. In this case, I'm asserting that the value that your function gave back or came back with is going to be within some tolerances, negative 1.2. Here it's false because I returned 0. Okay? So this is the reason that we give this to you is that you can actually actively test your code and see if you're getting the right answer back out. Yeah. No. I control all tolerances. No, unfortunately, no, because that would be modifying the tests. We don't allow you to modify the tests. Yes, that is a problem sometimes. It is one of the most difficult things to deal with in this class as someone having to write the questions. If there is something that needs to be corrected, I will let you know. If you're having troubles with the tolerances, let me know, and we'll try to get to the bottom of it. But yeah, it is a danger. In fact, another good example. What if I was clever and knew that I had to return negative 1.2? This one's going to be fine, but of course the next one, which is also a testing block, is not. Now, if I was really clever and started looking at what I was inputting, like, oh, if I was input negative 2 and 3, I should give out that type of thing. We are looking at your code, so do not do that. That would give us a lot of 0 points on your score. We would not be happy. But that's kind of how this stuff works. Here's another type of test. So this is actually testing a corner case, where in here, if there's a statement that says return the computed sum, make sure to include a way for the function to exit if the partial sums do not satisfy the above criteria. So that just means compute the sum and then oh, here it is. Returns the computed sum and raises a value error if the sum appears to be diverging. So that's the raise value error parentheses business. And this is checking to make sure that that happens. Okay? So if you have questions about this type of thing, we're just trying to get you exposed to some of these ideas. Let us know, and we can talk about it during office hours. Yeah? Correct. That does work. It won't say a thing. Which, come to think of it, usually I will say something, success, or you, yay, or congratulations. Not in these, apparently. I was being not so generous. But yeah. So here's another example. This is actually one that we're not actually doing tests for. We just want you to write the code, and we'll look at the answer. So sometimes we'll do this, especially in plotting questions. Here's a question where we want both a mathematical answer and a code answer. So we'll grade those. And some more plotting questions. Yes? It's mysterious, isn't it? I deleted question 4 before I released it and forgot to increment or decrease the number on 5, which was always the question 5. There is no question 4. Sorry. I thought about saying it was a ghost question, but then I didn't want to worry you so much. All right. Yeah. No. Not really. Eventually, once you stop the Jupyter Notebook interface, it will stop the kernel as well. So it's not that big of a deal. Eventually, if you did it enough, it might be a big deal, but by and large, it's fine. Okay. I'm going slower than I usually do. Let's just do the introduction of numpy here. Okay, so numpy is actually the library we're going to use the most, by far. Numpy provides us, at its core, something called the ND array. It just means an array. And it acts like a matrix, it acts like a 3D array, and it does things very, very fast. So let's jump right into it. Import numpy. That's how you import numpy. Some people do this, which is another version of import statements. You can do this. I generally don't, but I'm also trying to be the pedantic faculty member, trying to make sure everything is very clear. Doesn't really matter to me. Just don't use import numpy as np and import numpy, because then we'll be in a world of hurt. But you can do that in general for import statements. If you have some long name for something you're importing, you can always rename whatever that namespace is to that. But here we got import numpy. Here we're going to define, very MATLAB-y. Any of you have used MATLAB. We're going to create a numpy.array, and it's going to be 1, 2, 3, 4. Okay, so this is one of the rows, and this is the second row, like that. So it looks like nested lists, like we were using before. And then we index into this, like you would expect. So the 0, 1 component of the array is going to give me back 2, because it is the 0th row and the first column, again, indexed by 0. So 0, 0 would give me 1. 1, 1 would give me 4. You can also find columns like this. So you can again use the colon operator. Now we don't have to provide it anything. It just means all the values. Actually, we could have done that before, but it's kind of a little silly. So here we're saying I want the second row and all the columns, which gives me the row vector 3, 4. Okay? We can define column vectors. So here's how you do that. I will say, although I'm actually being super careful about column vectors, row vectors, and things like that, NumPy doesn't care so much about it's not going to strictly check for you, which is both a great thing because then you don't have to worry about too much, but it's a bad thing when things go awry. So just be aware of that. It does check sizes. If it doesn't think it can multiply something, it will tell you, but it will try its hardest to do things for you when it probably shouldn't. So be aware of that. But we can also do all sorts of different operations. So here is actually numpy dot dot. It's a little bit of a mouthful, but it is the dot product, or it's just multiplying some matrix by a vector. So then it actually checks all sorts of things to make sure this works. So this is going to be my array that I defined before, and the true product, matrix vector product, with my vector. The reason why I'm making point here is that if you use an asterisk, the multiplication, it will not do a proper matrix vector product. Okay? What it's going to do instead is it's going to take that vector and multiply that column vector into the columns of the matrix, and it'll give you back a matrix instead, not a vector. Okay? So this is actually very different from MATLAB. Just be aware that this is the case. If things are not quite working in terms of sizes of things, this is probably why. We're going to revisit this a lot when we start talking about linear algebra. So it won't come up too much until then, so don't worry about it too much, but keep this in the back of your mind. Also, there's a cross product. So there you have to have two vectors, and it'll give you the right thing. And you can also do things like question mark. So here's actually a better example of a docstring. So numpy.cross, let's return the cross product of two arrays. A and B are the arrays. You can add all sorts of crazy axes things. So this would be if you wanted to multiply bunches of vectors that were all in some array all together and you wanted to slice it in certain ways. This is what you do with it. It gives you a big explanation of what's going on, explanation of the parameters, whether they're optional, what if it's expecting, what it returns, what it raises. So if it ever raises an exception, you know what might that exception be. There's other products, so inner outer product. We may use those. That's exciting, I don't even know. And there's some notes and some examples. So this is actually very typical of a NumPy function. So if you're ever curious what's going on or how to use a function, usually there's a lot of documentation. So you can see there's a huge number of examples here. In fact, even using some of the more complicated entries into this. Okay, so, I did have an example. This is when you do my array times my vec. You see that the vector was 1, 2, and it's multiplying 1 times 1, 3 times 2, 1 times 2, and 2 times 4. And that's what it's giving back, instead of the actual dot product, which should be a vector. Okay, so just be aware of that. So next time we're going to finish up with NumPy and some plotting stuff, and then we'll start in on error discussions. So have a good weekend. Hopefully it becomes cooler. And I'll see you next week. I haven't done the weight test yet. You haven't done it? I have not done the weight test. I'm not up to that. And I accepted the weight test at the beginning of the year. So you will only find out if you're off weight test at 9 p.m. on weekdays and at 6 p.m. on weekends. So you will. I will update.